So yes, thanks for having me here. I'm Chief Product Officer and co-founder of VoxelSensors. Let me first give a few points about VoxelSensors. So we are a Brussels-based company. We co-founded VoxelSensors in March 2020, so just before the first lockdown. Today we are 20 people, mainly located in Brussels, but also we have a couple of folks in the UK and the USA. We are VC funded. We raised up to 13 million euros for the seed round. We invented the Sparse, so the single-photon active event sensor technology, which I will introduce today. We have up to date 82 patents, 29 granted and 53 pending. And we are focusing basically on creating novel technology, which is low power spatial sensing and eye tracking for XR perception. So let me just quickly recap on what are the challenges in spatial awareness or spatial computing as we see it today. So we need first to have a system, let's say, that is low power, high resolution, and low latency. Because we plan to run on AR devices, and these devices need to run for the whole day, let's say. So we need to be very low power, and also we need the low latency in the 3D mapping of the world, because we want to have to minimize the lag between the digital world and the real world to have a meaningful experience. The second point is that we need an accurate and robust system because the quality of the depth data that is acquired directly impacts let's say the user experience and the quality of the function. And of course, if you think of multiple users wearing a similar AR headset, these headsets needs to work together and not to interfere between each other. So we need a 3D system that is capable of working in any light condition, but also working with other headsets or other systems running at the same time. The third point is that all these systems need to be miniaturized and a very small footprint because the XR trend or the AR trend is going to smaller eyewears, wearable devices, a bit like what the Ray-Ban Meta is doing. So this is the kind of devices that are envisioned in 5 to 10 years from now. So every technology that is integrated there needs to be miniaturized. And the fourth point is that any system that is integrated today, as we see it, needs to be multifunction. So all the OEMs want to have a sensor or a system that is capable of doing more than one function. So let me talk about what we are actually doing as a system. So this is a very basic principle of our system and how it works. So on the first hand, we have a laser beam scanner. So basically today we are using a 2D MEMS mirror that is shining one single laser dot across a scene and generating a Lissajous pattern with one single laser dot. And on the receiving side, and this is our core IP, where our core IP resides, this is our invention, is the single-photon active event sensor. Its aim is to detect the laser dot position at a very fast rate, which means that in tens of nanoseconds, the sensor reports the laser dot position in the scene and sends out this XYT position, which means that on the processing side, if we know the laser projection vector at any given time and also where it is seen by our unique sensor, we can triangulate this laser dot position in the scene, and hence we create a new 3D point at a very fast rate. So every 10 nanoseconds, we have a new 3D point in our depth map or in our point cloud. So our system is not a frame-based system, but is a serialized sequential system where we provide a new 3D point every 10 nanoseconds. And recapping again on our sensor and system requirements. So what we want is to have a low optical power because we want to detect the laser beam with the minimum photon budget. and therefore we use a SPAD as a primitive device in our pixel array. We also need a certain density in the acquisition because we are using MEMS that vibrate at a frequency of 20 kilohertz, for example, which means that if we take our current sensor, which is a QVGA resolution, we know that the laser dot will spend less than 100 nanoseconds on each pixel. And then we need to be able to detect this laser dot position very fast with a few photons. And therefore, we use a SPAD. We also need to work in all ambient conditions, which means that we implemented very specific on-chip circuitry that we patented, of course, to be able to isolate our active photons coming from our active illumination from passive photons, from, for example, ambient light or thermal noise of our sensor. And hence, we call our technology an active event sensor. And at last, we want very low sensor power. And the only way to do that is to reduce the relevant data that we transmit out to the processor. And that's why we chose the event-based readout. So in the end, just to recap, on the front-end side of our technology in the sensor, we're using a SPAD device in order to achieve low optical power, but also a low bandwidth and high speed of detection. And on the back-end side, we're using an active event readout type of data. So if you look a bit at what the signal that we are looking at the scene looks like. On the left, we have our active photon flux, which is basically this laser dot moving at a certain rate in a Lissajous pattern. And of course, if we are operating in a regular ambient light condition, we will have not only this active photon flux, but also an ambient photon flux, which means that our active illumination is kind of lost in a sea of photons. So if we pass that into a SPAD array or a SPAD device, this is the kind of detection that we might get. So you can see that we have a lot of different triggers, basically across the whole SPAD array, triggering on ambient light, on thermal noise, but also on our active illumination. Actually, you can see this active illumination on the screen on the right, moving into this sea of photons, of noisy photons. Then, what we implemented in order to isolate the active light from the passive photons, from the noise, we have an on-chip in-pixel spatial and temporal filtering, which is our creation once again. And this means that at the output of our front end, so at the output of our SPAD array, we're able already to isolate the active light from most of the noise. But still, on the right here, you can see that some of the noise, some of the unwanted events are passing this filter. So what we have after the front end, so after the SPAD array, we have what we call our event stream filtering, which basically also operates on the fact that we know or we understand that we are looking for a continuous trajectory. So we know that what are the precedent events. We know where to expect, let's say, the laser dot to move according to the known trajectory, and therefore we can really filter the active light, let's say, from the ambient noise. And then we output, so the sensor outputs XYT, which is a address event representation of the laser beam pattern. So just to recap on the full flow then, we start by analyzing or looking with our sensor at the scene, which contains not only the active photon flux, but also the ambient light. This triggers a lot of SPAD events, SPAD activations in a certain time window. We apply an in-pixel spatial and temporal filtering to first reduce the noise and extract the active light. And after that, we have another on-chip event filter after the SPAD array in order to increase the SNR and extract only the meaningful events that we transmit afterwards to the to an output processor, let's say, in order to do the triangulation and get a depth map or a point cloud. Now, in order to achieve a true low power and low noise system, we use at system level another trick, which is knowing where the laser beam projector is supposed to shine, let's say. So, for example, if we apply an epipolar constraint at system level between the sensor and illumination, we can already predict in which tranche, in which region of interest of the SPAD array we expect to have the next active active laser light falling, and therefore we can activate only the portion of interest of the SPAD array, and therefore reduce dramatically, as you can imagine, the power of the sensor and the power of the system. And this is where, or what we have today. So we started first by applying our Sparse technology for 3D sensing. Today we have the second generation of evaluation kits, which is deployed at many of the OEMs in the XR industry. But our solution is not only a fit for 3D sensing. We are also addressing other use cases like eye tracking, OptiTrack, and so on. So this is, by the way, what you can get out of our SDK. So what you see here is a depth map and a point cloud of the scene. And the hand here, by the way, is the hand of our CTO, Ward van der Tempel, who was supposed to give this presentation, but he's in a train right now going to Vision Stuttgart, where we also have a booth. So if you are also there and interested in learning about VoxelSensors, please feel free to pass our booth. And so to recap, today we have two evaluation kits that we are providing, two different evaluation kits that we are providing to customers, Andromeda 1 and Andromeda 2, which are based on our first silicon. And we are also deploying later this year a miniaturized version of our technology, which will have a MIPI CSI2 output that we are also planning to integrate into very interesting ecosystems early next year. That's it for today. Thank you for your attention.